Okay, first of all, I want to introduce Onur Mutlu. He was born in Kayseri, and he started his bachelor degree in Bilkent University. And with a scholarship, he moved to US, and he got 2 bachelor degrees in Michigan University, computer engineering and also psychology. And then he obtained his PhD and master degree from the University of Texas at Austin with the title Efficient Run-Ahead Execution Processors, which is implemented in commercial microprocessors as well. And he has both industrial academic experience. He worked in Microsoft Research and had different positions at Intel, AMD, Google, as far as I know. And he started as a member in the CMU in 2009, then moved to ETH Zurich in 2015. And he received numerous prestigious awards from academic communities and industrial companies. And it's very important, his computer architecture course videos and materials and all the research outcomes are publicly available online and used by many people in the world, including myself. Yes, Onur Hocam, you can continue. Thank you.
Okay, yeah, thank you very much, Işıl. I appreciate the introduction, and yeah, I'm glad that you're using the videos. I think we met for the first time when I gave a summer school lecture at Boğaziçi University, right?
Yes, yes, exactly. This is the first time. Yes, yes, and it was very inspiring. And after that, I just became one of your followers, actually.
Oh, that's great to hear.
In different areas.
Yeah, that's great to hear. This was in 2013.
Yes.
Yeah, 7 years ago. Yeah, I actually recently uploaded. I didn't upload, but those lectures were on YouTube.
Yes,
and I recently put them on a playlist on my own lecture list.
Okay, okay. I can remember these days.
Yeah. I think they're good recordings, actually.
Yes, yes, yes.
Yeah, actually, some of my friends who are like big deal people at Google watched some of those videos, and they were surprised that in the middle of the lecture, people came into the lecture and brought chai. Turkish chai, because those are on the videos also.
Yes, part of our life.
Exactly, yeah. They were asking if it was common practice in Turkey to bring chai to the lectures. I don't know if that's true at your school right now, but
yes.
maybe not right now, but before this pandemic.
Yes, by the students or by the instructor even, it's a good practice, actually.
Yeah, exactly. I think some people get surprised because it's not common in the world.
Yes.
Okay, so thanks for inviting me. I think I can get started, right? Okay, so yeah, again, thanks for inviting me. It's great that I think your classes started this week, right? And
yes, this is the first lecture.
Okay, yeah, this is the first lecture. Okay, yeah, yeah. So this is essentially our class started last month, and this is the first lecture that I used in my class last month. So I'm going to essentially deliver the same lecture, if you don't mind.
Yeah, it's a really great pleasure.
Yeah. Basically, I will try to go over architecture is so important and exciting today. It was always exciting for me, but I think today it's exciting for many people. So hopefully people will appreciate it. So I see a delay. Okay, so I'm going to skip the introduction slides. Thanks, Işıl, for the introduction. You can reach me in this email address. You can find my website also. I guess in addition to what Işıl mentioned, I also worked at VMware for about a year before I moved to ETH, like a sabbatical. So I like working a lot with industry, especially on understanding the research problems and solving problems. I will give you some examples. So I do research and teaching in computer architecture, computer systems, hardware security, and bioinformatics. We especially focus on memory and storage systems, hardware security, safety, predictability, fault tolerance, hardware-software cooperation. And we're looking a lot into architectures for bioinformatics, health, and medicine. Can you hear me very well?
Yeah,
Yes.
we can.
Okay,
Yes,
that's
we
good.
can.
Okay, so it's just a problem with the delay of the slides, I think. Now I'm on the next slide, but you don't see it yet. Now, okay.
Yes, I think there's some delay, but that's
Okay. Okay, that's good. As long as you hear me fine, I will adapt to the delay. So this is what I'm really excited about, basically building fundamentally better architectures for many different goals to make our lives better. I work in computer architecture, hardware, software, co-design, systems, bioinformatics, and security, as you can see over here. And this is just one picture of it. We essentially touch all of the components that you see over here and many more. This is just a single node, as you can see, but there is a bigger system associated with it. These are 4 key current directions that we're examining. How do we build fundamentally secure, reliable, and safe architectures? And I think this is really important, especially because we're building architectures that we're going to rely on even more in our lives. How do we make our computing systems more energy efficient and fundamentally energy efficient? Meaning, how do we ensure that we do not move data in systems so that we can have sustainable computing going into the future? This is very important, I think. We'll talk about that. How do we have a much more lower latency and predictable architectures? I think this is really important, as we can see with the screen sharing right now. You can see that there's a latency delay. And I think we need to fix issues like this going into the future. And how do we build much better architectures for important workloads that we really care about, like medicine, health, genomics, artificial intelligence, and machine learning? So we are working on all of these directions today. And I'll give you some examples of it, but I'll also give you examples of what's happening in the computing architecture industry as well. So before we start, this is the transformation hierarchy that I introduced in my lecture. So we build computers to solve problems, but clearly we cannot solve problems by just talking to electrons, right? Computers work with electrons. We don't have a way of actually telling electrons, electron 1, please do this, electron 2, please do this, electron 3, please do this. That's not going to work. Instead, we build up a hierarchy. We build devices out of electrons, and then logic gates out of devices, and the microarchitectures out of logic gates. And then we communicate with the microarchitecture through a well-defined interface called instruction set architecture, or the software-hardware interface. And on top of the software-hardware interface, we have system software, languages, algorithms, and then we eventually have to translate our problems to the algorithms. That's how we can really talk to the electrons today, actually. And all general-purpose computing systems work this way. Special-purpose computing systems eliminate some of the parts. Over here, for example, you may not have a software-hardware interface that's well-defined. In an FPGA, field programmable gate architecture, you can directly translate your algorithm into the microarchitecture that you have designed. But there's some sort of transformation hierarchy, and this transformation hierarchy is very good so that we can keep sane and enable programming of the devices much better. But it also imposes some challenges, as we will discuss. So what is computer architecture? Computer architecture is really, traditionally, it has been limited to the software-hardware interface, the instruction set architecture, and how it is implemented in the microarchitecture level. It normally doesn't even go into the logic. But I take an expanded view of computer architecture in my courses, and also I think, as I will show you in the examples that I will provide, today's computer architecture is really much more expanded. They span all the way from algorithms to devices, and all of the levels of the stack or the transformation hierarchy are covered inside the architecture. And this is very important, I think, to high energy efficiency and highest performance that you want. Okay, I'll animate the entire slide so that you can see it very quickly. Okay, it'll take some time. But basically, this is my axiom. To achieve the highest energy efficiency and performance, we must really take this expanded view of computer architecture, because we cannot just say, okay, I care about the interface and the microarchitecture. We cannot just say, I don't care about the software. You really need to co-design across the hierarchy, co-design the algorithms together with the logic and the microarchitecture and the devices, so that we can specialize as much as possible. So one example is if you want to build a really high performance machine learning accelerator, like it's been happening in industry today, you really want to customize your algorithm to the underlying logic and devices so that you can get the highest efficiency. If you go through a very general purpose interface and you don't optimize across the layers, then you get inefficiency in the system. So I'll give you some examples of this as we talk in this lecture. Okay, before I jump into that, let me talk a little bit more about what we do in my research group. Essentially, I said we build fundamentally better architectures, but we really take this expanded view. We really go all the way from algorithms to devices. So we have broad research spanning applications, systems, logic, with architecture at the center of it, of course. And these are some of the things that we look at. We look at designing data-centric architectures for low energy and high performance. This includes processing in memory, non-volatile memories, as we will talk about, and unifying memory and storage systems. Low latency and predictable architectures. How do we design memories that are very low latency, low energy, yet they're still low cost? How do we make systems much more predictable and quality of service aware? And as I mentioned, I'm very interested in fundamentally secure, reliable, and safe architectures. How can we tolerate bit flips? How do we build much more patchable hardware in the field? And how do we make memories much more secure? And I already said this also, how do we build architectures for machine learning, artificial intelligence, genomics, graph analytics, and medicine? And this requires really what I just said over here, basically. You have to really go from all the way from algorithms to architectures and logic, and you do the co-design and make systems much more heterogeneous. And last thing was not on previous slides, but we also want to make architectures much more data-driven and data-aware, meaning architectural controllers today. So if you look at my cell phone over here, I'll show it, but I don't know how long it takes for you to see it. But my cell phone is 5 years old. It doesn't matter even if you get a new cell phone today, it has controllers in it, and these controllers are making decisions, but these controllers don't learn from their decisions. For example, as humans, we are very good at learning. We can, of course, always do better, but normally we learn quickly. If I have my hand on a hot surface, I quickly figure out that it's not a good idea to put my hand on that hot surface again. If the surface is cold, I quickly figure out, oh, it doesn't matter. So I can quickly learn based on the environment and the rewards and the punishments that I get from the environment. I can learn what to do in the future when I see that similar environment again. But unfortunately, that's not true for the devices we design. Actually, all of these algorithms that are employed in the devices, in the hardware, they don't learn. So the memory controller in this cell phone, for example, is making the exact same decision in the same circumstances over and over for 5 or 6 years. And I think this is something that's not very good because if the architecture itself can learn, it can optimize itself over time. And I think this is something that's really required going forward. I call these more intelligent architectures, and they have to be data-driven, meaning they have to use some learning to change the policies dynamically in their architectural controllers as well as design. Okay, I'm not going to talk about this as much, but keep this in mind. This is actually a very exciting direction, I think. How do we really build an intelligent machine? And I don't believe that any of these machines are intelligent because they're really lacking a key concept, which is really learning from your actions. So the software machine learning systems, they can learn things, but the hardware itself is not learning from its actions. Okay, and the last one is data-aware architectures. I'm going to give some examples of this. We want to communicate more information from the higher levels to the lower levels of the stack, like I described over here, so that we can really optimize things. Okay. By the way, if there are questions, feel free to ask me. I think I have a lot of material. I think I can cover the remaining time of the lecture, if that's okay. But feel free to ask questions also. So this is my research group. I'm going to talk about some of the research that's done by my students. You can see there are quite a few. And this is our motto, and you can find information about us. Okay, this is I'm going to give you a little bit about my perspective before I go into talking about computer architecture even deeper. But this is one of the principles that I follow. I think it's really important to understand that teaching really drives research, and research drives teaching. So whenever I teach, I also think about how we can do better in terms of systems. That means it drives research. And research also drives teaching, because after you find some new idea and it becomes important and becomes mainstream maybe in devices, then you can teach about it very well. And I think research and teaching are very important because they're two sides of the same coin. Meaning in teaching, you really teach what everybody knows, but hopefully you do it in a good way. In research, you do some research and you really teach the world what no one knew before. So you actually discover something new in research, and then you educate the world. So they're both part of education, in my opinion, and they're part of this endless cycle where education drives research and research drives education. And if any of these ends, I think then we have a big problem, basically. Then progress stops. And this is true, I think, in general, in any science and engineering, not just computer architecture. Okay, the other principle that is clear in my classes and my group is really focus on insight, and new ideas are really important. Again, if you stop producing new ideas, if you stop thinking about insight, then I think things become much less interesting, and progress stops. So progress really builds on insight, and new ideas. If you keep thinking about dogmas, old stuff, it's not interesting, right? That's not progress. Science is really building on new things and discovering new things. Okay, so these are some overview talks that you can find online. As Ishil mentioned, I put all my talks and lectures online. You can find some of them over here. I'm going to talk about some of these things actually during the course of this lecture, but you can find examples of this. And if you're really interested in knowing more about me and my perspectives, this is an interview that two Chinese students from Shuhai Qian's group did with me last year in June in ISCA, where we talked about many things related to computing research and education. And they were actually really good interviewers, I should say. They were very well prepared, so they kept me on my toes. And if you're interested, there's an award speech that I delivered last year also at ISCA that gives you a 10-minute version of some of those views. And there's more. If you're interested, you can watch that and look at these slides. Unfortunately, the talk about these slides is not online yet. Okay, this is not moving, I think. Yeah, I'm talking about this slide, but okay. Anyway, I'll wait on this slide for some time so that you can take a look. So these slides, I can send them to Ishil, and you can make them available, I assume, Ishil, right?
Yes, of course, I can.
Okay, great. Okay, so that's the introductory part. Now let's go into why study computer architecture today. Okay, so the first question is, of course, what is computer architecture? Computer architecture is the science and art of designing computing platforms. And as I said, I'm going to take a broad view of computer architecture. It's really the hardware, interface, system software, and the programming model. And I say it's science. I view science and engineering to be very similar. So it's really science and engineering at the same time. But it's also art. I don't think it's just science and engineering. It cannot be, because you're really designing some computing platform for, let's say, use in the field for 5 years, 10 years, maybe 20 years, 30 years. Some of the systems that are designed have been in use for 40 years, 50 years. So you cannot really predict into the future. Actually, if Apple is designing a chip right now, it's not going to be on the market for 3 years or so, right? That means that they have to predict what's going to happen downstream 3 years later. And as much as we would like to do that scientifically, it's just not possible today, because we cannot predict even 1 minute into the future, right? But 3 years into the future is much more difficult. So you really need to have a keen sense of art and creativity, and also a keen sense of thinking, such that you can see what's going to come down the road 5 years later, let's say. That's why I say it's art. And I think art is very important. And this is true actually for building architecture as well. If you're a building architect, you really need to think about the artistic aspect of your architecture. How long is your architecture going to survive and be beneficial to the humans, right? Okay, so why do we design these computing platforms? We need to achieve a set of design goals. And in the end, there are many design goals. I'm going to animate these quickly so that you can see them. But there are many different design goals also. For example, one design goal could be, I would like to obtain the highest performance on Earth on 3 workloads, X, Y, Z. You can pick your favorite workloads. So it could be nice things like climate modeling, so that you can fix the climate problems, or COVID-19 modeling so that you can fix why this is happening. Or it could be bad things like development of an atomic bomb, right? So the science and technology are always agnostic to morality in the end. Morals are completely orthogonal to science and technology. You develop science and technology, you can use it for good, and you can use it for bad. Hopefully you use it for good in the future so that humanity becomes better, but clearly you cannot guarantee that, right? Okay, but my point over here is some workloads are extremely demanding, and you may actually want to get the highest performance on Earth on those workloads, and this is the design goal of a high-performance supercomputer, for example. And there are supercomputers designed. I'm going to show you pictures of that. Or you can, this is part of computer architecture, designing a supercomputer from all the way from its software, programming model, hardware, software interfaces, logic, devices is computer architecture really. Or designing a system that has longest battery life at a form factor that fits in your pocket with cost less than some amount of dollars or Swiss francs is another example goal, right? Design goal, right? You can see many things go into this, right? Cost, battery life, form factor, temperature, probably thermals, because you don't want this device to burn your hand. You want to keep it in your hand. So there are clearly many things over here that go into the design of this device. Okay, so the other, so that's a complete different device. This is a complete different computing architecture than the first one, clearly. Here we're talking about a cell phone, for example. Last one is also another design goal, which is I would like to get the best average performance. I don't care about the highest performance. I don't care about the longest battery life. I want to do as good as possible on average across all workloads that I care about, as many as possible, while providing you a best performance cost ratio. Right? And this is another design goal, and this is also computer architecture. So Intel and AMD, for example, have been designing computers for decades with this goal. These are called general purpose computers. And they're essentially, the general purpose means they're designed for a general purpose. And whatever I described over here is general purpose. And they're not best at anything, but they're good at almost everything on average. That's the idea. So they're hopefully not worst at everything also. So you can see that these are 3 different design goals, and there are many systems that have been designed with these design goals, and you can imagine many other design goals over here. So clearly, these are all computing architectures, and designing a supercomputer is different from designing a smartphone. But in the end, they all have similar principles. Let me do something over here. Okay, this is what I wanted to do, because I want to see how it appears on your screen also. Okay, this is much better right now. Sorry. Okay. Okay, I'll dismiss this. Okay. Okay. Yeah. Clearly, designing a supercomputer is designing from a very different from a smartphone, very different from a general purpose laptop, for example. But many fundamental principles are similar. And computer architecture looks at those fundamental principles, as well as how do you actually design systems so that you can actually achieve these design goals. So now let me give you some pictorial examples of this. It'd be better if our connection was faster, but anyway, so these are some platforms, as you can see, that you use probably, that you know of. This is another platform that we didn't talk about, but this also has a computer architecture in it, and it has very stringent design goals. Well, this is a drone. You're not seeing it yet, but you'll see it soon, hopefully. Okay, I don't see it on my computer. Do you see it? Okay, there it is. Yeah, basically this is a drone. It's a computer architecture again. It has very different design goals, as you can see over here. Because you really want high battery life, high efficiency over here, and also a predictable performance. Okay, if you go to next one, this is a self-driving car. Clearly, this has different design goals, and this is clearly a funny picture of a self-driving car, right? Ideally, we would like to be able to trust these things so much that we would be as happy as this person while driving this car, but we're far from it today. But clearly, this has a lot of other design goals like safety, security, and they're going to be increasingly more important. Reliability. If you get a tire problem over here, what happens? Do you die immediately or do you survive? There are many questions over here, and reliability of the other people around you. So these are actually exciting applications of computing architecture going into the future, I think. And this is one example of a self-driving car. This is one of Google's earliest self-driving cars. I'm on the next slide, but you will see it soon. And this is the infrastructure that you can see that goes into doing the decisions to enable the car to self-drive. So it's a huge computer, basically. And it may actually communicate with the data center also. So it's not very good, actually, to have such large computers inside your car, clearly, so that you can have accurate decisions as to how to drive, so that you don't hit someone or yeah, exactly, basically. So this is a problem, basically. How do we actually enable these systems to be much more efficient going into the future, such that we don't need to have very large, unsustainable infrastructures that look like this? And at CMU, while I was at CMU, CMU was actually doing a lot of work on self-driving cars. And this was around 2008 and 2009, 2010 or so. And they had a similar system. This was CMU BOSS. This is the driving challenge that was there in the United States. At that time, actually, if you looked at the back part of the BOSS, it had, I think, 16 big servers inside it. So clearly that's not sustainable, right? So that you can actually execute the machine learning and vision processing algorithms to do it well. But this is exactly why, one of the reasons why computing architecture is becoming much more important and exciting today, because all of these important applications that are being designed, like self-driving cars, drones, robots, etc., they're all dependent on much more efficient and high-performance processing. And clearly, we don't want that processing to be 64 servers, huge data centers. We really want them to be much more efficient going into the future. And that's exactly why people are looking into what I said, algorithms through devices and making things much more efficient across the stack. Okay, so we're going to talk more about that. I'm going to give you real chips that were designed for this purpose. So this is another platform. You can see that this is a data center. I believe it's a Google data center, but it doesn't matter. All of the data centers look similar at some level. But you can see that here, the platform design is for a completely different purpose. You don't have a single application. Your goal is not to do self-driving in this data center, but your goal is to really execute many applications possible in an energy efficient manner. And again, some part of the data center may be specialized for some applications. Some part of the data center may be specialized for some other applications. But again, it's a huge system. And power considerations are important. Cooling considerations are very important. Energy is still important. High performance is still important. And cost is very important also. But data centers are a bit problematic today because they're consuming a significant fraction of entire system energy in the world, maybe 2 to 3% actually, and it's growing. So we have a lot of problems with data centers today. Why? Because we're relying a lot on data centers. Like when I send an email, unfortunately, it goes through data centers. When I send a text message, it also goes through data centers. So there's a lot of problems, I think, in the design of our systems today that needs to be solved so that we can become more sustainable. Okay, so this is another example that looks similar to the data center. You're going to see it soon, but it's completely different. So this is one of the fastest supercomputers of the world. It's Tianhe 2 from China. I don't know if it's still the fastest. It used to be the fastest a couple of years ago for sure. I'm not sure if that's true right now. But this system looks like a data center, but it's designed for high performance on just a couple of applications, scientific applications, like climate modeling could be one of them, or molecular dynamics is another one, for example. How do you do scientific computations much faster with this? And I think there's a lot of opportunity with these as well. But the goal is performance. So cooling is important still, but cost is less important compared to the previous data center, because here you really want to put a lot of money so that you can get very high performance in some applications. I just said cost is less important. I didn't say unimportant. So cost is always important, actually. If someone tells you they're designing a system and cost is not important, talk to them 5 years later or 2 years later, they will tell you cost is important. So this is very fundamental again. These design constraints there, cost is there, security is there, performance is there, energy is there, cooling is there, thermals is there. So there are many, many design constraints in the system. But how important the different ones are compared to each other changes depending on the design of the system. I don't think in the end, none of them are unimportant. It's just a prioritization of which one is more important and which one is less important. Okay, so let's go into a little bit more. So this is actually the Tensor processing unit that Google designed around 2014 to 2017. It's called TPU. And the goal of the system is to specifically accelerate machine learning, specifically neural networks. deep neural networks or recurrent neural networks. This was designed, this shows you that today companies like Google are also designing hardware so that they can accelerate applications. Why? They found out that their machine learning algorithms are too slow and too energy inefficient in their data centers if they're executed on CPUs or GPUs. And they said, oh, we want to design specialized units, and we want to co-design our application and the software and the system as well as the hardware together so that we can get the highest efficiency in our systems. And you can see that this system is actually a systolic array. You may see systolic arrays in Işıl's lectures. I don't know. I haven't studied what she's going to cover. But I cover systolic arrays in my freshman course, for example, in digital design and computer architecture because they're so fundamental. What these systolic arrays do is they take data inside, and data flows inside this processing units, and then data gets outside, put out the memory. And this is a concept that was invented at CMU actually in the late 1970s. The idea is to minimize the data movement, data accesses to memory. So what happens here is you do matrix multiplication in this array, and while to do the matrix multiplication, you fetch one data element only once, and the data element actually traverses through the array, and then it gets written back. So you actually maximize the computation that you do per memory access in the systolic array. And this is actually a lot of fun, I think. A lot of machine learning accelerators today work this way. I'm going to show you some more later on from state of the art. This is not the state of the art right now. You can see that this was released and this paper was published 3 years ago, and Google actually improved their accelerators going into the future. But this is an example of an architecture that's inspired by biological principles, actually, when H.T. Kung, who was the inventor of the systolic arrays, wrote his paper in 1982, actually. It's an IEEE computer paper, and it's titled Why Systolic Architectures. He said that computing architectures should be designed similar to how the human blood system operates. Basically, you have the heart in human systems, right? And the heart pumps out blood, right? And a heart clearly does not communicate with every single cell. Think of the cells as computation units of your body. Heart doesn't have connections to every single cell. Every single cell doesn't go to the heart and ask, oh, can I have some blood, right? It doesn't work that way. The way it works is heart pumps out blood periodically. Think of the blood as data. And that blood goes through the cells, flows from cell to cell through the veins. And eventually, the blood that's polluted goes back to the heart to be cleansed, right? To become clean. So this is very similar to that principle. Because if actually every single cell asks the heart for blood, can you give me some blood? Because I need to do some processing here for a vital function. That's not going to work because that interconnect is not going to scale, and heart cannot scale also, right? Because then millions of cells in your body is going to ask the heart for this blood. And clearly, you cannot scale the memory bandwidth, meaning the blood circulation bandwidth that way. But if heart periodically pumps up the blood, pumps the blood, and the cells operate on the blood and then pass the blood to each other while they're doing operation, it's much more scalable. So you can see that this is a fundamental principle of human design, let's say, applied to computer design. And I would recommend reading H.T. Kung's Why Systolic Architectures paper if you're interested in it. Okay. So we're going to talk more about that. But you can see this is another different platform. This was actually a platform that was designed by Tesla, which is a self-driving car company. Even though it's a self-driving car company, it's designing chips, as you can see. In fact, it has one of the best computing architecture teams in the world. And this was designed, I think, last year, 2019. You can watch this YouTube video where they actually talk about how they designed this. And actually, Elon Musk also talks about some of the architecture over here. He introduces a lot of the architects in this. Basically, they designed these chips so that they could customize their self-driving car algorithms and execute them efficiently on their hardware design. So why didn't they use a GPU? Why didn't they use some other hardware accelerator or FPGA? Well, the answer is very simple. Because they know their software really well. And if they design the hardware also together with their software, they know that they're going to get the highest efficiency in this case. So they don't want to rely on some other company to actually produce this hardware for them. So there are many companies today are producing hardware, and they're really doing research across the stack. So the computing architecture is becoming even more exciting today for this reason, because we're really seeing that real energy efficiency and high performance comes from designing software and hardware together, as you can see. So you can also see interesting things here. So you can see the number of transistors, 6 billion. It's not a lot, actually. And you can see it has CPUs, 12 CPUs, 1 GPU. It also has 2 redundant chips. So all of this is replicated twice. Why do they have redundancy? Because they want safety in their system. So if one of the chips fails, they can continue using the other chip. That's the idea over here. This is called dual modular redundancy. It's a very fundamental concept in dependable system design, and Tesla is already employing it. And you can see how safety is important. Clearly, this is very bad for cost, right? You're using 2 chips to do 1 function, which is self-driving. But unfortunately, it's so important and so safety critical that you want to actually have the overhead of dedicating 2 chips for it. Okay, so this is clearly a different platform with different design goals. Okay, so what is computer architecture? I'll define it a little bit more over here. Essentially, it's the science and art of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system that meets different goals. These goals could be functional, performance, energy consumption, cost, and other specific goals. And essentially, there are many different types of computing architectures that are designed today. That's why it's really exciting, I think. There's a lot of heterogeneity in the field. So if you're doing research in computing architecture in, let's say, 1990s, it was a bit less exciting. For me, it was always exciting because I find all of these topics very fundamental and very important going into. But in the 1990s, Intel and AMD were dominating the field, and they were designing processors in a very fixed way. It's essentially superscalar, pipelined, out of order execution. Many sophisticated single-thread performance enhancement techniques. Even NVIDIA was not there. Even GPUs were not that important. But over time, things have changed. And today, computing architecture is really important. And there are many different types of architectures because people figured out that the design that was done in 1990s that was dominant, the single-thread architectures, cannot really be the answer for all of the workloads that we have. And they're not scalable going into the future. So essentially a revolution, let's say, happened in the late 1990s, early 2000s. People had to move to multi-core, and then they quickly figured out that multi-core is not the answer to everything. And then right now we're in the middle of a revolution, let's say. Computing architecture, there are a lot of answers that people are seeking in terms of what is the best architecture for different workloads. And the answers are still out in the open. So you can actually do a lot in computing architecture today to contribute to the field. Okay, I'm going to talk a little bit more about this if you have time, but if you don't have time, you got my shorter version. So, okay, that's why I think looking at computer architecture with this narrow view is probably not a good idea going into the future. Although these are fundamental, clearly, knowing the ISA and knowing the logics is microarchitecture is really important, but always considering all the way from algorithms to devices is much more important. So that's why we're going to take the expanded view, and we're going to talk a little bit about that in this lecture. Okay, so of course you may have the question, why do we want to study computer architecture? Hopefully I've given you some examples. Basically, we would like to enable better systems. We would like to make computers faster, cheaper, smaller, more reliable, safer, more secure, etc., whatever you can imagine. And the goal is to hopefully enable a better life. But again, as I said, technology is always agnostic to ethics or morality. So you cannot. We can only hope that these will be used for the better, of course, and hopefully help people to use it for the better, and maybe not help for the people who don't want to use it for the good of people. Anyway, but the goal is to exploit advances and changes in underlying technology and circuit, essentially, and also adapting to new applications. Okay, the second one is enabling new applications. I think this is really important. So computer architecture has been and hardware overall has enabled many new applications, even though we may not think about it. For example, the reason why machine learning today is so important, and everybody talks about machine learning, most of the people are excited about machine learning, is not because machine learning algorithms are new? It's because the hardware is fast enough to execute those algorithms. So if you look at machine learning, all of these deep neural networks were invented in 1980s in seminal papers by Jeff Hinton, for example. And they, of course, refined it. But until 2012, nobody really thought that these would be realistic. In 2012, some of Jeff Hinton's students, and Jeff Hinton wrote a paper, it's called ImageNet actually, and they basically showed that using GPUs, they could actually do inference in these machine learning networks, and they could do it fast. And this really changed what's happening in machine learning. They basically said this new hardware enables us to actually execute these neural networks really fast. As a result, now everybody's doing machine learning almost. So never forget that the software was there, but it got enabled because the hardware became fast enough. Essentially because GPUs became mainstream, and some folks who were doing machine learning got excited about them, and they said, oh, we're going to use these GPUs to take advantage of machine learning algorithms and execute them fast. And that's essentially what, that's how machine learning applications got enabled so far. And that's true for other things like self-driving cars, because the hardware actually was fast enough to execute these applications. That happened. Graphics is an older example, actually. The reason why we have visualization that's so good is because we have hardware engines that can do graphics really well. Cell phones are another example. The reason why these cell phones are really good today and are available today are because we have flash memory that can fit into our chip, fit into our the form factor like this. Imagine using this with a hard disk. You cannot carry a hard disk, right? Inside this, because hard disk itself is bigger than what I'm carrying right now. So it's really all about the hardware that has enabled all of these new applications, and the performance improvements that have been happening in hardware and computer architecture for decades and decades have enabled many applications. And I think going forward, we will have even more applications like virtual reality. I think that's going to be more important. Telepresence is another application. Right now, for example, I'm giving this lecture online. But we could do much better, right? Potentially, you could see me next to you in a class. We could all be in a class potentially, and we could all be interacting with each other with our avatars. Let's say, if you watch the movie Avatar, that's an example of how you could be interacting, right? That's an example of virtual reality. It's not there yet because we really don't have the computational power, but people's imaginations are there. But we cannot do it today because computational power has not really been there, but all of that computational power will really come from computer architecture. Personalized genomics is another example that I have in mind. Personalized medicine. I'm going to talk about that. We do a lot of research on this. Wouldn't it be nice so that I could have my cell phone be my doctor, right? And then I don't need to deal with a lot of issues related to, I don't know, many things clearly. Okay, so this is very important and exciting, clearly. And I think the third one is also related. It's enabling better solutions to problems, maybe not necessarily new applications, but better systems. As I said earlier, software innovation has been built on trends and changes in computer architecture. And for a long time, performance has improved by more than 50% per year in hardware. And that has enabled better software and better innovation. And clearly, more specialized hardware like GPUs have enabled new applications. Now, more specialized hardware like Tensor processor units or self-driving car processors, they're enabling new applications also. Okay, I think my fourth point over here is we would also want to study computer architecture so that we can understand computers work the way they do and fix problems that come up and design much better machines going into the future. So understanding is also very important. And I think we need to do more of that going into the future. So as a scientist and an engineer, I think understanding is really the first step, right? We should really understand how things work so that we can build better systems. Okay, so as I said, today is a very exciting time to study computer architectures because industry is in a large paradigm shift to novel architectures. As you can see, I showed you several examples. I'm going to show you even more examples from industry. There are many different potential system designs that are possible, and people are considering all of these new architectures, and some of them are being adopted. And there are many different reasons, difficult problems that motivate this paradigm shift that causes, and that are also caused by the shift. So clearly applications, there's a huge hunger for data and new data intensive applications like machine learning. like health applications. And also at the bottom layer, we have issues like power, energy, and thermal constraints. It's fundamentally becoming difficult to make our circuits power efficient because we reduce the size of the circuits to be very small. And as a result, things are becoming more difficult to improve at the lower level. I believe there's more potential, but while things are difficult to improve at the lowest level, computing architectures can help a lot, actually, because you can actually take advantage of every single transistor and keep it efficient. You cannot waste any transistor, basically, today. Complexity of design is becoming much worse today. So people are trying to solve how to build simple systems, and designing, again, across the stack helps. Again, difficulties in technology scaling. I'm going to give you some examples of this. Basically, we're getting bit flips in memory today that leads to security problems, privacy problems, safety problems. How do we solve those issues? That's why industry is examining new architectures again. Memory is a huge problem. Accessing memory takes a lot of energy and a lot of performance. And how do you actually solve that problem? This requires a paradigm shift, I think, as we will discuss. Reliability problems are getting worse, again, because circuits are getting worse at the lower level. They're becoming more vulnerable to the noise. And there are many, many noise factors today, especially if you go to space, for example. People are exploring going to space for many reasons, but reliability problems will become much worse. There are issues like how do we better program our systems? I'm not going to talk a lot about these, but this is going to be also important. And we will, you need better computing architectures to make programming easier for many people. And security and privacy issues are becoming very important also in applications like genome sequencing, for example. But even in general purpose systems where you have bit flips due to technology scaling, your security may be compromised a lot. And people care a lot more about security today, or I think they should care a lot more about their security today going into the future. And this is a difficult problem. So clearly, there are no clear definitive answers to these problems at this point. That's why it's a very exciting time, actually, to study computing architectures to enable these things. Okay, and these problems actually affect all parts of the computing stack. So this is my computing stack. I also put the user here. That's not the newest picture, but user actually interacts with many parts of the system. But actually, they interact with more depending on who you consider to be the user. They could be the algorithm designer also here. But basically, there are many new problems that are happening today in the workload space. There are many new issues at the bottom, at the electron level, physics level, circuit level. Things are not scaling very well. There are reliability issues, energy issues, scalability issues, complexity issues. So an architect needs to look down and understand what's going on here. They need to understand what some new technologies, for example, which we will also talk about. They need to understand the problems and algorithms at the higher level. So they need to be open-minded. So some people are dreamers in the world. These are really people who want to change the world, and they design applications. For example, I think self-driving cars is one example. Space exploration is another example. Like a completely different way of designing brain-machine interface is another example. So these are very different problems. And I think a good architect actually looks up and understands those problems and tries to enable them. And also, users are also changing a lot. Clearly, there are a lot of demands coming from the user, and personalities are also changing, and there are different types of users. So again, the architect needs to look up and understand the user as well. So again, there are no clear definitive answers to all the stack. So as I said, computing landscape is actually very different from 10 to 20 years ago. 10 to 20 years ago, Intel was very dominant. Today, that's not true. That's why Intel is also suffering a little bit. They're trying to adapt to the new computing architectures. But things are essentially different. Software and humanity trends, technology and their issues, and the resulting requirements and constraints. So essentially, the architect needs to look up, look down, and also understand the past, look backward, and understand the future also, look forward. Okay, so today, every component and its interfaces, as well as entire system designs, are being re-examined. And these are some components in the system. And it's very exciting, I think, because we're really re-examining. If you have some new idea in any of these components, you can influence the world. So we do research in all of these areas, and I've seen our ideas go into real products much more easily today compared to the past. In the past, I'm going to give you some examples over here. Okay, that's why I think we have this axiom that I already said to you. I will animate this relatively quickly again, but basically, we need to take the expanded view and really consider all the way from algorithms to devices, co-design across the hierarchy, and specialize as much as possible the systems that we design. So I think of this as, so for example, if you're a dreamer, let's say you have the software and there's this really nice application. I don't know, it could be, for example, a brain-machine interface where your brain gets signals and understands the environment really well, and it can actually give you hints as to how you should speak, or maybe it speaks for yourself, right, in some other language, right? It does online translation, right? How do you design the system, right? Clearly, you will need to go from all the way from an algorithm to devices. If you would like to fit this on your body, let's say, I'm not suggesting into your brain, but into your brain could be another possibility. But if you want to fit this device on your body so that you can do online translation and speak at the same time, this requires a device that's able to do everything over here, all the way from the algorithm to devices, because clearly if you go through a data center to do this online translation, it's already a non-starter because the latencies will kill you. So it's not going to be feasible. That's why I think that's another example application that I just dreamed of, if you will. And everybody wants to have online translation capability without hopefully learning a new language, right? Learning a new language is nice, but we don't have time in the world to actually learn many new languages. And this is an example application where computers can be extremely useful. And I'm not talking about Google Translate. I think Google Translate is good, but it's essentially useless for me when I'm going to speak with someone online. If I want to deliver this lecture, for example, in Russian, it's not going to happen with Google Translate, right? Okay, so let me give you some more history a little bit over here. So if you go back to this computing stack, lower levels, logic and devices, they're actually really important. Electrons, they're actually really important. So I don't know how many people know this phrase, there's plenty of room at the bottom. But a lecture, this is really a famous lecture that was delivered by a famous American physicist, Richard Feynman. He was a Nobel Prize winner also. And he had a very lucid way of thinking about things in the world. He's also a very good educator, in my opinion. But he delivered this lecture in 1959, as you can see over here, more than 60 years ago now. And basically, what he said over here is bottom matters, bottom of the stack, meaning physics, electrons. All of these things matter a lot. And we can innovate a lot at that level so that we can make computers much better going into the future. So the talk is really about computing. How do you compute with better use of the devices that you have at the bottom? And he basically considered the possibility of direct manipulation of individual atoms, as you can see, as a more powerful form of synthetic chemistry. And this talk actually was largely unnoticed until 1980s. And in 1980s, people finally started working on nanotechnology. Nanotechnology means these are devices that are at nanoscales, very, very small devices. And they basically said, they basically discovered this lecture. And they said that, oh, this lecture is really important in terms of its visionary value. And you can see Feynman was a dreamer in this lecture. You can see that he basically talked about the general ability to manipulate matter on an atomic scale. And that's what bottom means. Can we manipulate atoms in a much better way at that scale? And he was particularly interested in dense computer circuitry, microscope that could see things much smaller than is possible with scanning electron microscopes. I'm just reading from this Wikipedia article, as you can see. And later, these visions were realized by different devices like scanning tunnel microscopes, atomic force microscopes, etc., and storage systems like millipede. These are actually nanoscale storage systems. You can take a look at those. And also, he suggested that, in principle, you can make nanoscale machines that can arrange the atoms in the way we want and do chemical synthesis by mechanical manipulation. So these are actually really fun topics, I think. But these also show that there's a lot of stuff at the bottom that you can still do. And another thing over here is some other vision that he has, for example, swallowing the duck. It's essentially building a tiny swallowable surgical robot that operates on your body. Now, people are trying things like this today, actually. It's very interesting, but we're not there yet. These robots are not good enough. They're not efficient enough. And again, computing architectures to build such robots is going to be very, very important. So there's still plenty. I still believe that there's plenty of room at the bottom. We can do much more at the lower layers by looking at new technologies, pushing the boundaries of energy efficiency, pushing the boundaries of performance in the circuits. and devices. Clearly, I'm not a circuit level or device level person. We do work in touching the circuits, but I think enabling these circuits to do better is a lot more. Now, unfortunately, some people don't think that there's plenty of room at the bottom. I completely disagree with them. I think today we're hitting scaling the existing circuits and devices at the lowest levels because things are very small today. But I believe there will be breakthroughs where we can actually go into much smaller circuitries, much more energy efficient circuitries. Quantum computing could be one of them. But even before we go into quantum computing, I think there are things like carbon nanotubes, for example, that could enable us to go into much smaller geometries. I think there's more innovation in the lithography of the devices that is going to happen. And I believe there's more innovation that will happen in chemical computing and biological computing also, as we understand biology and chemistry much better at the atomic scale. I think that's why I think there's plenty of room at the bottom. So I don't believe those people who don't think, who basically think that, oh, circuits are done, we should just focus on software. I don't believe that's true, actually. And I believe Feynman, if he lived, he would probably agree with me even right now. Okay, so this is another paper. This is actually a relatively new paper written by a lot of folks from MIT, saying that there's plenty of room at the top. Essentially, these folks make the argument that circuits are becoming difficult to scale, so we should focus on software and architecture. And I agree with this point of view. I think they're not saying it's impossible to do something at the circuits. They're saying it's becoming difficult. That's why I think we should also focus a lot on the architectural level, computer architecture and software. And you can see that maybe some of the words are too strong. For example, unfortunately, semiconductor miniaturization is running out of steam as a viable way to grow computer performance. There isn't much more room at the bottom. I disagree with this statement. But it's true that it's becoming much more difficult. If growth in computing power stalls, practically all industries will face challenges to their productivity. I agree with this one. Nevertheless, opportunities for growth in computing performance will still be available, especially at the top of the computing technology stack, software, algorithms, and hardware architecture. And I absolutely agree with this one. Basically, this is saying that software, algorithms, and hardware architecture are becoming very, very important so that we can get much better performance out of energy efficiency out of our systems. And I think that's going to be more important in the future. But I think it's really, in a sense, I would revisit both of these articles and I would restate everything as, I believe there's plenty of room both at the top, meaning software, algorithms, and architecture, as well as at the bottom, meaning logic, devices, electrons, and who knows what else. But I believe we can do much better, meaning we can get much more room if we can communicate well between the top and the bottom and optimize across the top and the bottom. And I believe today's computer architecture is really about this, communicating well between software and the lower level hardware and the devices, and taking advantage of both things and optimizing across the stack. That's why we have this expanded view over here that I'm going to talk about more. So hopefully that gives you a historical perspective also. Clearly, there are folks who are thinking about the bottom and the top, but I would embrace both and say we really need to think across the stack. Don't think too much about the top and the bottom, but let's get these cross-layer designs do well.
Onur Hocam,
yes.
Can we have a short break at least to have to take some questions?
Yeah, sure, of course. I think this is a good point actually. As you can see now, I'm going to go into examples. So do we want to take questions? Feel free to ask.
Okay, I know you can talk for hours without stopping.
That's correct. Yes, that's correct.
Which is I cannot do. And if there are some questions, and we can also during this time, I guess.
Okay, sure.
Do you have any questions? I think we can discuss in Turkish as well. If it's
yeah, sure. I don't see any chai coming though. That's fine, sure.
Can I ask something?
Okay.
How fast do you think the adoption rate of these new technologies will
be? Which ones? Like the quantum computing or carbon nanotubes? Is that what you're thinking? Yeah, so I think new technology is a very general word. But if you're thinking about, I think, quantum computing, I think it will depend. I think it's going to have its place, meaning I think it's going to be used as an accelerator. But I don't think it's going to replace all of our computers. That's my thinking. But I think it's going to be adopted for sure in some problem domains. Some other technologies like emerging memory technologies, non-volatile memory technologies, they were a dream for us more than 10 years ago. I'm going to give you the story of it in a little bit. But today they're already adopted. So new technologies, I think, will at some point be adopted. But it's very hard to, of course, predict when. So, okay, let's look at some old examples like flash memory. Flash is why I have the cell phone, I think, and why I can carry my laptop everywhere, literally everywhere. And flash memory is actually a technology that was developed in 1970s, but it didn't really have its impact until 2000s. So that's 30 years if you count the number of years. 30 years is a lot, but it took 30 years to get it adopted, right? But once it got adopted, it really revolutionized, I think, everybody's lives in the world, because I don't think people would be carrying these cell phones if flash memory wasn't inside them, because DRAM is not enough, clearly, for storage. So I think I'm a believer in technology. I think if a technology is good for some applications, and if it's really solving a problem, I think it will eventually get adopted. Of course, it's very hard to guess how long it will take. Does that make sense?
Yes, thank you.
Okay, so I'm going to give you some examples from our own research as we go along in a little bit. Okay, other questions?
Onur hocam, we cannot see you.
Oh, okay, really?
Yes.
I don't know. I didn't
Okay.
really. No, I did. Oh, you can see me now? Hello?
No.
No.
Okay, I don't know why. Wow, automatically I think my screen turned off itself. Let me try to do something.
Okay.
I didn't do anything, but
Okay.
yeah, I cannot.
just thought,
Okay, interesting.
I just thought.
Oh, okay. When I'm sharing the screen,
from the
I see.
other.
Yeah,
Yes.
when I'm sharing the screen. Okay, I'm going to turn off my screen sharing. Then, can you see me now?
I see myself.
Okay, let me turn my.
No, it
Okay.
does not.
How about now?
On.
Yes.
Okay,
We can see.
because it told me that I cannot my video. I cannot turn on my video without sharing my screen. It says
Okay.
while sharing
Okay.
my screen. Yes. Mm-hmm.
Okay, I see. Maybe it was about the web browser. I don't know. Okay,
Yeah,
at
maybe.
least-
Sorry.
no, that's okay. At least for the questions
Sure.
part.
Yeah, sure. Sorry.
I just wanted to tell this. Okay. Any other questions? And I can ask a question.
Sure.
Yes, you showed these layers in the computer system. I'm also using the same slides in my courses, actually.
Okay,
I'm trying
that's
to adopt this.
Sure, that's great.
And it's a kind of very new for the especially beginners, because the people are missing this interface. Okay, this is a subject which is related to hardware, or which is a subject which is related to software. So we have, especially as the beginners, we have this difficulty to connect these layers. What is the best? Okay, and the computer architecture, for example, in our curriculum, it is almost the only course we have this opportunity. What are the other things we can do to fill this gap?
Yeah. To basically enable people to see the connection between different layers. Yeah. I agree. I think in general, computer architecture courses are actually the best places to discuss this. I mean, if you're a beginner, okay, I don't see myself also, but I don't know why. My camera is on though. Okay, I see GoPro. That's not mine. Okay, but I can also turn on my other camera on my other computer to see if that one actually also works. Okay, so I have two of myself right now. Okay, maybe you can make. Okay. Anyway, so basically, I think as a beginner, I think you really need to look at all of the different parts. So in your course, for example, you can probably cover different portions to show examples, but I think you're asking beyond your course, right?
Yeah, exactly.
Yeah, I think beyond your course, I would suggest, for example, students doing some projects would be nice. For example, if they take an algorithm and implement on an FPGA. I think that then they can see these layers much more nicely. Or implement on a GPU. That's another place. That's where I would suggest students to do these things actually. So these hands-on, I think there's no substitute to doing this hands-on, frankly. And if you do these things hands-on with implementing on an FPGA, implementing on a GPU, then I think you can see it much better.
Yes.
So maybe, yeah, maybe you can offer some courses where the students can do it.
I'm already offering heterogeneous parallel programming course as a technical elective. Yes.
Okay, that's great.
And I'm trying to teach the GPU programming. Yes, it's a more hands-on course, and it's a technical elective, and only 10 people are selecting out of 100.
Yeah. Yeah, that's probably, I think that's probably normal if it's an elective, right? If it's a required course, you will get more people, clearly. Yeah. But it's an elective, yeah.
But we also have artificial intelligence course we are offering this semester, and I think 50 or 60 people are there.
Yeah. So I think,
yes.
I think in the artificial intelligence course, for example, some of the projects could really go into how do you design accelerators for some machine learning algorithms. Because that's really the really exciting part in systems today. If you go to, for example, Google, Facebook, or whoever, Amazon, if you ask them what's the limiting part in their systems, they're all really designing accelerators to accelerate these algorithms that they come up with, and they have to fit the algorithms to their accelerators. So I think even artificial intelligence courses can can have a component where students go across the stack.
But we could just find time to provide the fundamentals, nothing related to interconnections and the relationship between these. We are teaching the algorithms in the AI course, and we are teaching the GPU architecture or specific components in the other course. But yes, this part is missing, and maybe we can also add this kind of lecture or course in our departments, if I talk specifically for our departments.
Okay, sure. Yeah.
Thank you. And you have also given this kind of project and seminar courses this semester. I think it started this semester in your department.
Yeah, exactly. We have several projects of seminar courses where you probably saw 2 of them are on accelerating genomics or mobile genomics. 2 of them are on DRAM and Remulator, hands-on, and one of them is on processing and memory. Exactly. Yeah. So they're all hands-on courses.
Yes.
And it's
very interesting.
Yeah, and it's right now it's limited to a small number of students, but in the future we may offer it to be larger.
Yeah. For example, this might be a choice, but yes, we should find more interested students in Turkey as well, I hope.
Yeah, I think that's the most important part. Hopefully students will be inspired and excited more after lectures like this.
Yes, exactly.
Yeah.
Okay. Any other questions?
I think Ercüment wants to ask a question. Go ahead, Ercüment.
Hello.
Hello.
First of all, I want to thank you that you're giving this speech, and my question is about the data-driven devices that you mentioned earlier. One of the biggest concern of our time is privacy. We spend a lot of time in online, and we use a lot of we spend a lot of time in computers and smartphones, and our data is going public somehow. And if the devices start to learn our behaviors and collect our data, is it it's making people that concerned about the privacy? Your research seeing that the concern, and what is your place in this about this issue?
Yeah.
I hope I make myself clear.
Yeah, it's clear. Thanks. Yeah, that's a good question, basically, and that's a tough question. It's not an easy answer, I think. And you're absolutely right. I think if devices start getting exposed to your private information and then learn on it and maybe send it somewhere else, you have a serious concern with privacy, and that's absolutely true. The key is basically figuring out how to do it efficiently, but without destroying your privacy. And I think, this is something that we're tackling in our research, especially right now in terms of genomic data. For example, if the device knows your genomic data, how do you actually make sure that it doesn't expose critical details about yourself to the world? And I think this is a problem that we're looking into. I don't think there's a solution, absolute solution yet, but I believe actually minimizing data communication is one way of reducing privacy problem. If you actually have a device that belongs to you and you secure it somehow and you ensure that the data doesn't get communicated outside of the device without your permissions, etc., and you have enough computing power to do almost everything energy efficiently in that device, then I think by definition your privacy will be better to begin with. But of course, you need to design the algorithms to be privacy preserving. So this is, you talked about a very difficult area, clearly. It's even more difficult than performance and energy, I think. So there are a lot of people looking into privacy preserving machine learning, for example. But I think it's not just about the algorithms here. Again, algorithms are part of it. But how do you actually treat your data in the system? Where does it get stored? How does it get stored? Is it encrypted? Do you obfuscate it so that people cannot actually read it, for example? How do you make things securely accessible in the memory? All of these issues go into the privacy question. And again, we're not there yet at this point, unfortunately. Unfortunately, our systems are very bad in terms of privacy and security today. But going into the future, I think by doing research, hopefully we'll have much more private systems. So that's one of the exciting topics also, actually, in computing architectures today. How do you design much more private systems?
Thank you very much for your answer. I hope there is a perspective that says privacy by design.
Yeah, and exactly.
And I think this perspective could lead us to better privacy. And another question is that if, for example, we have a device that collects our data and learns based on this data, how come for example, I buy a second-hand device, and this device, if we reset it, it starts from scratch, and this could be, how can I say, given this, how can I say, if this learning starts from scratch, this device has no meaning. For example, if I'm starting, I hope I make.
So if the learning, you said if the learning starts from scratch, the device has no what?
No memory.
No memory.
Example, for example, I buy a second-hand device, but if the privacy issue, because of the privacy issue, I clear the device and sold it that way. And this device starts from scratch, and this, for example, this feature of the device will go away. It will, and I have a suspicion that if it goes that way, and the device has no meaning. Do you think that way, or am I wrong?
So I didn't quite understand you. The device has no meaning, or
this device don't have any
memory
features. If we clear the memory, but if we minimize the data communication.
Mm-hmm.
By time, this device has no data or learning process.
Mm-hmm.
And this is the question that if we start that way,
Mm-hmm.
how can we make this large scale?
Yeah, so I think the problem is more than just clearing the device, right? Clearing device is nice, yes, but over time, devices collect a lot of information and they communicate with each other, right? And whenever you communicate your data, it gets exposed. So it gets used by someone, for example, it can be seen by someone. As a result, I think it's not easy to learn at the same time be private, because you need to do communication across devices.
I understand, and thank you
Yeah.
very much for your answer.
Sure, but I think as you said, privacy by design, security by design, I think those are really important, and all of these need to really start from they cannot just basically, how do we make algorithms secure or private? It really has to be a system-wide problem. So even hardware at the very root, in its gates, for example, in its logic gates, need to provide some sort of security guarantees, and there's some effort related to that, but again, these are some new concepts. So computing has been all about performance and cost for a really long time, right? For, let's say, 5-7 decades. More recently, energy has become a bigger concern. And even more recently, security and privacy are becoming even more, well, security, let's say, has become a concern. Privacy is even newer than security, actually. So there needs to be more to be done. That's why it's an exciting topic, actually. Okay.
Thank you for your answer.
Sure.
If we don't have any other questions, you can continue if you wish.
Okay, sure. Let me continue then, if there are no questions. These are good questions. It's good to have that interaction for sure. Now let me share my screen. Can you see my face also or no?
No.
Yeah, I think whenever I share my screen, unfortunately, this thing goes away. Yeah, maybe it's related to the web interface, but I'm also sharing my face in my other laptop, so I don't know if there's a way of seeing it together. Yeah, I don't know.
Okay, it might be possible. Right now, we are okay.
Yeah. Okay, should I continue or?
Yes, but right now we cannot see your.
Okay, yeah.
Okay.
You can.
Okay. Yes, we can see the slides, but not.
Okay. Sorry. I think this must be. Yeah. This. Yeah. Next time
yes,
I will.
I think so.
I will try it, but I have an Apple MacBook, so maybe. Yeah. Sometimes these things don't work very well.
I don't know. Yeah, I'm not sure. I'm using Linux and it works, but
yeah. Yeah. With
that's
Linux,
okay.
it may work.
Okay. That's okay.
Okay, so let me talk about some cross-layer design examples. I think like privacy is another cross-layer design example that I'm not going to talk about, but I'm going to give you some examples of work that we're. Sorry, I don't know what happened. So for some reason it says I'm not sharing anymore. Okay, but I am sharing. Okay, right now it's good, right? Okay, it keeps going back. Okay, now I'm not going to touch that thing. Okay. So, but this is one example of how can you communicate semantic information from higher level languages and software into our hardware architecture. This is, Nandita was my PhD student. She did her PhD thesis on this topic. And she's an assistant professor at the University of Toronto right now. But the idea over here is really, can we communicate information about data much better to the lower levels of hardware? And I think this is really important going forward. For example, let's take the case study that Ercüment mentioned earlier. You have some piece of data that's really important to you, and let's assume that you consider that extremely private. Today, you cannot communicate that information to hardware, so that hardware doesn't give access to that to other people, for example, or somehow it doesn't get treated specially. But if you actually can label that piece of data, saying that, oh, this is really private piece of information, or this other data is not private, then we can actually do decisions at the lower levels in the hardware architecture. For example, you could encrypt that data specifically. You could not communicate whenever that data is getting communicated in some way through the network. You don't allow it, for example. That could be a very strong privacy policy, clearly. So you could actually do all of these decisions at the hardware level without trusting software with it, right? Because if you trust software, it's not easy. Whenever you trust software, people will write some software that's malicious. If you have the root of trust in the hardware, you need to know about the data and its properties. And this paper talks about exposing those properties into the hardware. So this is an example of how do you actually enable hardware to be much more private, let's say. But this example is not in the paper. I use that example because of the question that was asked. But there are other examples that you can use from the paper that talks about performance, for example. For example, if you know the compressibility properties of your data, where is that? Yeah, here. If the software communicates to you, this data is very compressible, this data is not compressible, the data type is float or character, or the matrix is sparse, or you have pointers, you have data indices, then you can actually use the appropriate compression algorithm for different types of data and hardware to get much higher efficiency. And this is just one example, as you can see over here. There are many, many other optimizations that you can do if you have this sort of possibility. Okay, so there's another work that Nandita and we have done with NVIDIA. The idea over here is to expose the locality properties of different data structures. Basically, how often you access a data structure, which data structures do you access it with, is it shared with some other threads? And we did this work with NVIDIA, and this work was published, you can see, 2 years ago. And NVIDIA is actually building this locality descriptor in their hardware architectures today. So you may actually program with something like this next year. This is another example, again, spanning the hardware software stack. So if you know about the vulnerability of your data, if you get a bit flip, for example, if you get a memory error on a bit, how important is it to your data structure, to your application? Will it crash your application? Will it cause a security problem? Or you will not even notice it because it will just get displayed on a screen and no one cares about a single bit changing on the screen. So if you actually know the different vulnerability properties of your data, you can communicate that information to the architecture, and the architecture can be much more efficient by actually taking advantage of these properties. For example, really critical data. If you get a bit flip on that data, your system will crash. You can store that on very reliable memory, right? And that reliable memory can be specially designed for critical data. Whereas not so critical data, you don't care about the security and reliability of very much. You can put it on memory that's not very reliable, that's low cost, and that's extremely efficient and low latency. As a result, that your memory could be much more efficient this way, right? Today, we don't distinguish about the properties of data, so your memory is very similar. It's homogeneous, but you can actually have a heterogeneous reliability memory, as you can see over here. This is another newer example from our research. Basically, we look at deep neural networks here and look at inference, and we find out that different parts of the network, neural network, has different tolerance to, again, reliability problems like bit flips. And the idea in this work is to actually, and a lot of these deep neural networks are actually very much memory bottlenecked. Whenever you're accessing memory, you're stalling, and most of the time you're spending on memory, most of the energy you're spending on memory accesses. So the idea in this work is to actually allocate the different types of data that you're dealing with in the neural network to different parts of your memory, where different parts have different reliabilities and different latencies and different voltage levels. So, for example, some parts are very fast, very low voltage, so very energy efficient at the same time, but they're not very reliable. So if your data type has very good error tolerance, you would map it to those parts. So you would gain performance and energy efficiency at the same time without losing accuracy in your network, because these parts can tolerate the error rates. So my favorite example of tolerating error rates is, and these neural networks actually have a lot of statistical error tolerance. So internally, a neural network has many layers, for example, and there are many input parameters, and there's a lot of redundancy in the input parameters. So if one input parameter is wrong, you can tolerate it because overwhelmingly other input parameters will basically eventually make the neural network infer the right thing. But of course, this needs to be a non-critical parameter. So if you look at, if you understand how this neural network works, you can actually co-design it with hardware, like we discussed over here, so that you can get much better energy efficiency, as you can see. And this is another example. This was also published last year with my students. As you can see, all of these are with my students. So they actually do the hard work. They come up with the big ideas, and I help them come up with the big ideas and help them make the work stronger, as you can see. But basically, this work looks at sparse matrix operations, which are employed in a lot of machine learning algorithms, graph analytics, etc. And this work proposes a new compression algorithm in the software level for sparse matrices. And the compression algorithm uses bitmaps and also hardware acceleration for that compression algorithm together, because bitmaps can be manipulated efficiently in hardware. And basically, it shows that you can actually have a much more efficient system, graph analytics system or machine learning system, if you actually co-design the software compression and hardware accelerated indexing. I'm not going to go into more detail, but you can clearly read the paper here. And this is another example of rethinking the, again, all the way from algorithms to not devices actually, but this looks at the virtual memory interface and how do we actually rethink it. I'm not going to talk about this, but this is a recent paper, as you can see. I believe there's a lot of efficiency we can gain if you actually rethink the virtual memory interface also. Okay, so these are some examples from our research. There are more examples that I didn't talk about, but let me give you some examples from what's happening in industry today also. Today is very exciting because there are many interesting things happening in the computer architecture industry, and I'll give you several examples. Let's categorize them. Let's talk about performance and energy efficiency first. So how many people know about this Intel Optane persistent memory? I don't know if people can raise hands. Clearly, I cannot see if people are raising hands. Does anybody know about this? Okay, Ishil knows about it. Anybody else? Okay, some more people know about it. That's great. That's great. I can see people raising hands on my other screen. So I'm glad that I opened my other screen. But basically, this is non-volatile memory. This was released into the field by Intel in 2019. And basically, you can take this and plug in to where your DRAM is today. So you can see it's very high density, 128 gigabytes. And on top of this is non-volatile, meaning when you power off your system, your data doesn't go away. You don't lose data because this is persistent. It's non-volatile. So this is great, right? Basically, it's like storage. It's very similar to storage, but you can use it similar to DRAM also, meaning it's bidirectional storage. And it's, in terms of speed, it's much better than flash. It's a little bit worse than DRAM, fortunately, but it's there. So what you can do with this is you can manipulate files directly inside this persistent memory. That's one advantage of it. And you can get rid of a lot of the software overheads in manipulating files. For example, we have written a paper about it in 2013, for example. I don't have it here, but you can look at my publications if you're interested, or you can email me. That talks about manipulating files directly without going through the file system. And this work has enabled it. And this work is just for the first instance. Going into the future, the manufacturing technology will be much better. So you will, I believe, see 1 terabyte DIMM module that looks like this very soon, and maybe even 4 terabytes. So it's going to be, I think, very, very exciting going into the future. So this is based on what's called 3D X-point technology. Intel calls it 3D cross-point, and it's a general technology. Internally, I think it's phase change memory, even though Intel doesn't publicly admit it. If you actually know the literature really well, know the history really well, you would know that this is phase change memory technology. And phase change memory technology is very exciting. This is essentially a resistive memory technology, very different from existing DRAM. And it takes advantage of the fact that material exists in 2 different states with two different types of resistance. I'm not going to go into detail. I actually cover phase change memory a lot in my lectures. But this is something exciting because this could revolutionize how file systems are built, how operating systems are built, how applications are built, because now how systems are built, because now you have memory that that can keep storing data even after you plug it off from power. This clearly opens up new privacy and security problems also, because whenever you plug data off of your memory, you don't lose the data. So now it becomes a privacy and security issue also. So it's an exciting topic, clearly. And this has happened last year, just now. And actually, we were one of the first people looking at phase change memory as main memory. And you can see this paper that we published in 2009. We started looking at it in 2007 while I was at Microsoft Research, actually. And we basically wrote this paper saying that it's a good idea to consider phase change memory as an alternative to DRAM architecturally, so that we could replace DRAM with phase change memory. And you can see that the idea is from publication to building, it took about 10 years. Clearly, we didn't do all of the hard work that Intel did and other folks in the industry did, but we actually envisioned how you can get there. But of course, there's a lot of hard work in manufacturing that had to happen to make sure that the phase change memory cell could be manufactured reliably, etc. But you can see that the high-level idea actually existed actually 12 years ago, before Intel first released its chips. So this is exciting to me in computer architecture. You can see that idea, and you can evaluate it at the architectural level, show that there's a lot of potential benefit to it. And 10 years later, you see that somebody important actually builds that idea, and industry is actually now changed forever in terms of main memory. And if you're interested, you can take a look at this paper. You can also look at our special version of this paper that was selected as a special issue, because there's a special issue that's there in computer architecture conferences, and they select the best papers from the previous year. And this was selected at the time. And we had titled the article, you can see, as phase change technology and the future of main memory. And we argued that in the future, we will have phase change technology in main memory. And you can see that happened 10 years later. Okay, so this answers the question a little bit in terms of new technology, I think. I think it's good to always believe in new technology and evaluate it architecturally and at a systems level with workloads and show the potential benefit. And hopefully, the idea will become reality in the future. And I'm really happy that this idea became reality, especially by Intel, clearly. But actually, phase change memory is now manufactured by many others. Samsung, SK Hynix, IBM, they're all manufacturing phase change memory. But Intel was the first to actually release a commercial product. You can buy what I showed over here in the market. It's a bit expensive. Unfortunately, it's expensive. I think it's about maybe $2,000 or more, maybe. But this is a new technology also. It provides you benefits. That's why it's costly. And over time, cost will reduce, like any other technologies, cost has reduced. Like for example, when DRAM was first introduced in 1970s, again by Intel, its cost has reduced over time. Clearly, DRAM is very cheap today. Flash memory, when it was introduced in the late 1990s for the first time by Toshiba, its cost was very high. Its cost got reduced a lot today, clearly. And I think the same thing is going to happen for this phase change memory technology also. But in the meantime, I think architects have a good role of enabling new technologies, as you can see in this work. And the work is not done. I think there's still a lot of work to be done in understanding how do you take advantage of phase change memory technology in applications, workloads, and how do you actually co-design it with the applications. Okay, let me switch gears. This is another thing that happened in 2019. How many people are aware of this particular chip? This is Cerebral chip. Again, you can vote by raising your hands. In this case, I don't see any hands raised, so that's good. So some people are going to learn something new, hopefully. I think this is also very exciting, actually. And again, I can point you to some of these talks in Hot Chips last year. This year, there were some other talks in Hot Chips. But basically, what is this? So you can see, okay, before that, this is the largest GPU in comparison. It has 21 billion transistors, 815 square millimeters, NVIDIA Titan 5 in 2019. In 2020, it might be different. And this is clearly much larger, right? You can see that the chip area is 46,000 square millimeters. That's a lot. This is like this big. You cannot see my video, unfortunately. If you see my other screen, this is like this big. You can hold it in your hands. It's like your face, right? Almost. This has 1.2 trillion transistors. And this is the largest machine learning accelerator chip that has been built so far. And you can see that it has 400,000 cores. The new version, I believe, has more than 400,000, maybe 800,000 cores. And cores are actually systolic arrays. These are specialized cores just for machine learning. And these folks at Cerebral, which is a startup company, they decided to build this chip to maximize the efficiency of machine learning inference and train neural networks, essentially. They said machine learning on GPUs, which are the fastest engines today, is good, but not good enough. Why not good enough? Because you're moving a lot of data between the GPU and the main memory, and GPUs are not specialized enough. We basically need a lot more area on a single chip. And how do we get that more area? Basically, they said they're going to take a wafer. This is a silicon wafer. Normally, what you do is you take a big silicon wafer and cut it into pieces. Cut it into pieces that are as small as a GPU, for example. They said, we're not going to cut it into pieces. We're going to use the entire wafer, silicon wafer, as our area. So in Turkish, for example, my favorite example is gofret. Gofret is the same thing as wafer, actually, in English. You have these gofrets, right? These gofrets are small. But really, the way they're produced is you have a big, huge gofret wafer, and you divide it into small pieces. And then Eti, for example, gives you the smaller gofrets, okay? It's the same thing. In chips, as opposed to having smaller gofrets, now we want to have a huge gofret. And in this big gofret, we can have many different processing elements. And that's the beauty of this. Not only many different processing elements, we can also have a lot of memory close to those processing elements. So we can be very, very efficient in our processing. That's the idea over here. They said we can have hundreds of thousands of cores, specialized for machine learning workloads, and very memory on the same chip. So they have a lot of SRAM memory, and I think it's 18 gigabytes or so. So this is a lot, actually. 18 gigabytes on chip is a lot. They can fit a lot of the data that's needed for machine learning on the same chip without going off chip. And that was their goal. So it turns out this is very efficient, but clearly there are a lot of interesting design issues here. So this idea was thought about in 1970s, 80s, 90s, and it was dismissed. Today, machine learning is so important of an application that people are designing very innovative architectures that look like this. But clearly there are issues here, meaning, okay, this is a huge chip. How do I power it up? How do I cool it down? So they design systems for cooling. They talk about how they cool it down. Of course, some of this is proprietary, so they don't give you a lot of details. How do I tolerate faults? So if I have 400,000 cores, at any given point in time, one of them may fail. In fact, the probability of failure of a core, if it's constant, you're going to see many more failures at a given time frame, right? So how do I tolerate those issues? So there are a lot of really, really interesting issues, architectural issues like this, that need to be solved to make it work. And Cerebral is clearly trying to make it work. Actually, they already have customers. Some of the customers have bought this because they're doing a lot of machine learning. And I think there's a lot of exciting stuff going on, as you can see. So this is another example. So this is an example of doing processing and memory very close to each other in a specialized fashion. So look at this other example. This other example is also in 2009. This is from a company that I work with actually very closely. It's called UPMAM. They're based in France, in Grenoble, relatively close to Switzerland here. And these folks are actually also very innovative. They basically put a processing engine, a simple CPU, in a memory chip. Why? They wanted to minimize the data movements between the processor and memory, which is a huge bottleneck today. And they have a programming interface to this, so they can actually do many, many operations concurrently across many, many memory chips today. And you can put this in your system. So we have examples of this that we're working on right now, actually, in our system. So you can see that this is a very innovative concept. People have proposed something like this, but it never saw reality until very recently. So why are we interested in it today? Because data movement is a huge bottleneck, and energy and performance are very important constraints, and workloads can take advantage of these devices that look like this. So clearly, this also is across the stack problem. How do I design algorithms for this? which is true for this also. How do I design algorithms for this Cerebrus's wafer scale engine? Which is also true for Intel's persistent memory. How do I design algorithms for it? How do I design architectures that can take advantage of it? How do I design compilers for it? How do I design system software for it? How do I design the architecture internally for it? So it's really, again, an across the stack problem. So it's cross layer. So there's a lot of other examples. So we do a lot of work on processing in memory. That's why I like this UPMEMS engine a lot. That's why we work with them closely also. But we do a lot of other work on processing in memory. This is an example. We actually want to modify the DRAM chips like UPMEM does, but in a minimal manner, such that we can do block bitwise operations. So this is one work. Actually, this is a longer version of a series of works that Vivek did as part of his PhD thesis with me. Now he's at Microsoft Research in India. And we wrote this long article that talks about how do you actually change the DRAM to do block bitwise operations efficiently, and what are some of the research issues going into the future. We actually designed processing in memory accelerators for graph processing, as you can see, for machine learning later on. And then we actually worked with Google to understand their workloads, mobile workloads better, and looked at processing in memory to minimize the data movement overheads in a mobile device that looks like a cell phone or a laptop. And you can see there are more works that we have done on low overhead locality-aware processing in memory. I'm not going to talk about this. But if you're really interested in processing inside memory, today's systems have a big dichotomy between computation and memory. If you want to operate on data, you need to access memory and bring all the data into a CPU chip. We say this is actually very inefficient. So we really want to actually do the processing where it makes sense, where the data resides. And data resides in the memory device, in the storage device, in the caches, while it's moving on the network. So we should really have the capability to do processing where it makes sense, meaning in the memory device, in the storage device. And the question is, of course, how do you do it? And what kind of benefits do you get out of it? And the benefits are actually a lot. You get more than 2 orders of magnitude speed up and perform energy improvement at the same time. So you can actually make systems much more efficient by making the systems more data-centric like this. So if you're interested, you can read these papers. These are actually high-level review papers, the previous one and this one, that appeared in our IBM Journal of Research and Development, as you can see. Okay, so let me give you some more examples. So as I said, Tesla is also building machine learning accelerators. I'm not going to talk more about this. I already said what I wanted to say about this, but it's happening, and it's a cross-layer design. This has also happened in 2019, as you can see. You can watch the YouTube videos. Google, even earlier, published their works on machine learning accelerators. Google was probably the first big company that did machine learning accelerators, as you can see over here. And again, this is the newer version of it. And they have even newer versions that they have not talked about as much. And this is the data center version, but they also have a version for edge devices like cell phones, smartphones, or laptops as well. And again, this is a systolic array, as I said. I'm not going to talk about this more. We don't have a lot of time, I think. But basically, if you're fundamentally, it's an architectural concept at the heart of it. They basically have a systolic array, which moves data, pumps data from the left and data out from the bottom. And it's a matrix multiplication unit. So you can see that a given 256 element multiply and accumulate operation moves through the matrix as a diagonal wavefront. They preload the weights for the network, neural network, and take effect with the advancing wave alongside the first data of a new block. And then they pipeline control on data to give the illusion that 256 inputs are read at once, and that they instantly update one location of each of 256 accumulators. So it's from a correctness perspective, software is unaware of the systolic nature of the matrix unit, but for performance, it does worry about the latency of the unit. Okay, and you can see the system design that goes onto it. And this is all computing architecture. You can see there they really call it matrix multiply unit over here. It's a systolic array. And the programmer needs to program nicely so that the data appears here fast. And you can see the bandwidth is very high. Here you have 167 gigabytes per second. Here you have 30 gigabytes per second. It can do a huge matrix multiplication, 64,000 per cycle. So you can read more about it in the paper that I mentioned from Google. But there are many other AI and machine learning chips that are being built. Clearly, these are some large companies that are building. And there are many others and many startups, and I believe there's many more to come. And you can see this is something that I found on the web that lists even more companies that look at machine learning chips. So this is the machine learning revolution. And don't think that it's really a machine learning revolution. It's really a computer architecture revolution that's enabling machine learning, as you can see over here. And initially, the revolution of machine learning in 2012 was enabled by computer architecture GPUs. Okay, so I talked about performance and efficiency. Let me talk about reliability and security, because this is really important. And clearly, there are a lot of interesting things that are happening in computer architecture today because we're having difficulties in both of these areas. How many people heard about the Rowhammer vulnerability? I will show a picture of this. This is DRAM Rowhammer. So good, multiple people. Well, Ishil doesn't count, I guess, but I see only one more hand other than Ishil, or maybe everybody else is sleeping by now and not listening to me. It's hard to tell with online lectures. Okay. So basically, Rowhammer is some vulnerability that we discovered with my students and together with Intel as early as 2012. We wrote the first paper on it in 2014. Essentially, this is the fact that you can cause predictable bit flips in commodity DRAM chips. And we found out that more than 80% of the tested DRAM chips are actually vulnerable. So I'm going to give you the story of it very quickly. Basically, whenever you hammer a chip, not with a real hammer, of course, but using software, using activates, you get bit flips. And you can induce bit flips predictably over and over again. And this is really the first example of how a simple hardware failure mechanism create a widespread system security vulnerability. So you can read papers about it that look like this. In the Wired magazine, for example, this folk has written, "Forget software, now hackers are exploiting physics." And I think this is a really good high-level characterization of what Rowhammer entails. Okay, so what is Rowhammer? So you don't need to know a lot about how DRAM works, but modern memory works by activating a row. If you want to read a row, read some bit over here, you need to activate the row, which means that you need to apply high voltage to this row, word line it's called in DRAM, or you need to open the row. Okay, if you want to access something else, you need to apply low voltage to that row. Now, if you keep, this is called a pre-charge and activate in DRAM, 2 commands. Now, if you keep doing this repeatedly, high voltage, low voltage, 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 enough times before the cells get refreshed, it turns out in some vulnerable cells and physically adjacent rows, you get bit flips. So if this was a 1, it becomes a 0. If this was a 0, it may become a 1, for example. Now, this should not happen clearly, right? We're not even touching these cells. We're just reading, activating this row. We're not even writing anywhere. We're just reading this row. We just keeping on doing this repeatedly. Now, this is happening. We call this the hammer row. We call this the victim rows. And we showed that you could induce these bit flips in more than 80% of the DRAM chips manufactured by 3 major manufacturers today. And there are only 3 major DRAM manufacturers today: Samsung, SK Hynix, and Micron. All of your memory comes from them. I mean, there is a very small fraction of small manufacturers, but it's unlikely that you're getting memory from them. But also they're vulnerable too, by the way. But basically, this is a technology scaling problem. All of these manufacturers hit the technology scaling problem because now DRAM cells memory cells are very close to each other. Whenever you access one row, you're disturbing other rows because they're too close to each other. There's fundamental circuit noise and electromagnetic coupling that's happening between the cells. So I'm not going to go into a lot more detail, but there's a good reason for it. Things are too close to each other. As a result, the circuit noise is affecting one cell while you're reading some other cell. But this is bad for security and reliability. When we first wrote our paper, this is the ISCA 2014 paper, we said that memory isolation is a key property of a reliable and secure computing system, and access to memory address should not have unintended side effects in other addresses. And we said that you could actually build a security attack that could hijack your system, that could basically become root and take all of your data and your system. And while we were working on it, these good folks from Google Project Zero did essentially that. They basically learned about the problem for our paper. They replicated the problem on their own systems. And they said they developed an attack that could take over the system using these bit flips. Now, I'm not going to go into the details of how this attack is. You can read their blog post. It's beautiful. It's linked from this slide, actually. But basically, what they do is they can circumvent all of the virtual memory isolation and protection mechanisms by inducing these bit flips in the right place in the page tables as a user level process. So you can run the attack, malicious program, and while the program is running, it induces bit flips carefully in locations that would give it access permissions to access all of your main memory if you were able to flip the bits. And they do the attack beautifully. And once you do that, all bets are off. Now you actually lose all of your system. Now, a famous hacker, so this is a very famous problem in security today. A famous hacker said, it's like Rowhammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations opened the door you were really after. And I like this, actually. This is a very nice analogy. Okay, so if you're interested in Rowhammer, this is our original paper in 2014. We recently were invited to write a retrospective about it, and I wrote it with my PhD student, Jeremy, who did his thesis on Rowhammer. And he was also one of the original authors on the Rowhammer paper. And you can read this. So this gives you a very good overall perspective of what has happened about Rowhammer in security, device, architecture communities. And actually, we have recently shown that these are all papers from 2000.
Sesiniz gitti şu an.
Hocam düştünüz ya da mikrofon kapandı.
Şimdi nasıl?
Şimdi açıldı mikrofonunuz.
Okay, pardon. Nasıl oldu anlamadım yani. Maybe I were. Is it good now?
Yes.
Okay, so let's keep going. So basically, here we showed that newer chips are even more vulnerable. Actually, if you're interested in, this is more of the device and circuit and architecture level aspects, which are really fascinating to me. So we examined more than 1,500 DRAM chips here and showed that they're becoming much worse. Here in the security paper, where we collaborated with some folks who are actually experts in security, we showed that so DRAM manufacturers, after we wrote our paper, DRAM manufacturers implemented some security mechanisms in their DRAM chips. And they said that Rowhammer is a solved problem. There is no more Rowhammer. And a lot of industry believed them. But in this paper, we showed that that's not true. Basically, we showed that you could actually overcome the mitigations that DRAM manufacturers put into their devices that they say they're secure. And clearly they're not secure, and you can see that this paper won the best paper award. You can actually download the applications that we've written. So unfortunately, Rowhammer is still a problem today, and it requires good minds to think about it securely. And there's another paper that we worked on together with Microsoft and MIT and showed that it's a very hard problem, actually. Rowhammer is a very hard problem to have a definitive answer to the question, is this DRAM module susceptible to Rowhammer, or is it free from Rowhammer? There's no definitive answer today we can give because it requires a lot of testing. And you could always design a better attack, like this trespass attack, like we've discussed in the previous work. Okay, how many people know about this Meltdown Inspector? I'd like to see more hands here because these were clearly more famous. Okay, I see more hands. Yes, that's good. That's good. Clearly, Meltdown and Spectre are more famous than Rowhammer. That's unfortunate. Maybe we didn't do enough marketing. So Meltdown and Spectre are also big issues, clearly, with processor manufacturers. Clearly, they got more attention, but Rowhammer is also getting more attention. I don't know why. I think this also points to the processor-centric view of the world. Whenever you have a bug in the processor, it's considered more important than whenever you have a bug in memory. That's unfortunate. I think Rowhammer is actually even more dangerous than Meltdown and Spectre because exploiting Meltdown and Spectre as a security attack is much more difficult, in my opinion, whereas Rowhammer is really easy. You just induce the bit flips and you can take over the system or crash the system, whatever you would like to do. Okay, but these attacks are actually interesting also. Essentially, someone can steal secret data from the system, even though, let me actually animate all of this. Your program and data are perfectly correct. It's not your hardware behaves according to the specification, and there are no software vulnerabilities and bugs. So this is different from Rowhammer because in your Rowhammer, hardware doesn't behave according to the specification, right? Hardware really should not have that bit flip. Here, everything is fine. There's no problem on the surface, but you still can lose your secret data because internally the processor executes speculatively. Now you will learn more about this in this course probably, but speculative execution enables the processor to look ahead and execute things that it's not supposed to execute. But in the end, processor executes correctly. If it's not supposed to execute something, it rolls back and it executes the correct thing. So it never exposes the speculative execution to the programmer. But while it's doing the speculative execution, it leaves traces of secret data in the cache, internal storage. So it brings data that's not supposed to be brought or accessed if there was no speculative execution. And recently, people figured out that you can write a malicious program that can inspect the contents of your cache, hardware cache, to infer the secret data that's not supposed to access. Now, this doesn't sound good. And as a result, Meltdown and Spectre became big issues. And people also showed that a malicious program can actually force another program to spec code that leaves traces of secret data. So you can actually induce some other program to leave traces of secret data, as you can see over here. So that also doesn't sound good clearly. So clearly, this is a problem. This is a problem because processors have been designed from a performance perspective, and speculative execution, caching, all of this was put inside the processors to get better performance. But security was not a concern. So essentially, I don't think there was anything wrong that was done. People just weren't thinking about security as a design constraint. So we can solve these issues by making security as a first-class constraint in design. And you can see this paper. This is, again, Google Project Zero was one of the first to discover this. And you can read this beautiful Project Zero blog post that talks about how to do this Meltdown and Spectre attacks. Okay, how much more time do we have?
Actually, after 10 minutes,
oh, we'll be done? Okay.
Lecture hour will finish, yes.
Okay, should I keep going or should I take questions? I mean, I will cover, I think, demanding workloads, which is also important, I think. And I think that'll be the end. After that, I will give you an overview of why it's interesting to be in computer architecture. But up to you. You're this, whatever you want.
No, it's up to you, actually.
Okay.
Yes, you can go, I think.
Okay, I can keep going then. Maybe if there are questions, I mean, we can schedule a special session of just questions also, if that's interesting.
Yeah, it's quite possible, yes, other than the lecture hour.
Exactly, yes. Okay, so let me keep going because I think this is also very exciting. I mean, I showed you a lot of demanding workloads, but I'm going to show you more. So clearly, machine learning, artificial intelligence is important, and they're happening right now. Graph analytics, graph processing frameworks, they're important. Databases, they're all important, and they're more demanding going into the future because data is increasing. But there's something that's really close to my heart, and that's really genome sequence analysis and genome sequencing technologies. And these are actually workloads that are, I think, are the workloads of the future. And we started this work as early as 2009. This is one of our recent papers in 2018. It's headed by my PhD student, Damla, as you can see over here. And we actually looked at these devices that you can hold in your hand. These are called nanopore sequencing devices. And you can see that these devices exist. They're actually really cheap. You can buy it for $1,000. That's really cheap compared to $1 million devices for genome sequencing. But you can actually sequence many genomes here. The problem here is that computational bottleneck is huge. So you can sequence genomes, but you can ask questions. Let's say, okay, what am I vulnerable to? Now that becomes a big computational bottleneck. So you cannot do it in the device. You need to send it to a data center. So basically here we analyze nanopore sequencing technology and tools for assembling your genome and then asking questions to it. And we find out that we really need to do a lot of architectural work in terms of the tools and the software and do the software hardware co-designs. Okay, so this is really interesting. Data becomes a huge performance and energy bottleneck in many workloads today, but genomes are actually, genome sequencing is another example where data is a huge bottleneck. And today, actually, we care a lot about this a lot more. I mean, when we first started looking into this in 2007, we said that we want to design a device where you could sequence the genomes in real time and do the analysis in real time. Basically, in 1 second, we want to get an answer. And we could give these devices to doctors, and the doctors can actually sequence someone's genome and then basically figure out a good treatment or figure out a good drug or ask critical questions in a critical moment such that they can apply the critical drug in a critical surgery, for example. For that to happen, you really need these sequencing devices to be fast and the analysis of the sequence to be fast. Today, we have another example, I think is maybe unfortunate. But I think we need to figure out how to deal with these things. But clearly, these nanopore devices are being used for COVID detection, actually. Very simple COVID detection mechanisms. And I think even more sophisticated COVID analysis as well. And you can see this was actually from 31st January 2020. There's a lot more going on in terms of sequencing, genome sequencing, both RNA and DNA sequencing in terms of COVID and as well as other diseases. But today, basically, these sequencing devices are great. As you can see, okay, I'm on the next slide, but I don't see it here. Yeah, these sequencing devices are great. They're not perfect, but we can get sequences very fast. But we're really bottlenecked by computation. After sequencing, you need to do read mapping. I'm not going to go into all of those steps, basically. You need to do read mapping, variant calling. These are actually things that you do to analyze the genome and compare to other genomes, compare to other things that you know about, drugs, etc. And in the end, that could enable scientific discovery, better medical treatments. But we're bottlenecked by computation today because of data. Data is a huge performance energy bottleneck today. Okay, but I think future is coming. When we first started working on it in 2007, again, we believed in the technology. This device didn't exist at that point in time. This device didn't exist. Now these devices exist. You can actually do something similar on your cell phone. So there's more to come, of course. You cannot do it fast enough. You can take the sample fast enough, but you cannot do the analysis fast enough. So we actually have been working on how to make the analysis much faster. You can see this is one work that we published in 2017. Mohammed, he was my co-advised PhD student at Bilkent University with Can Alkan, and this is his first paper looking at how to accelerate read mapping in DNAs with FPGA architectures. So this could be one project, for example, for people who are really interested in hardware architecture, maybe replicating some of these results. You can actually get the source code also. And this is Mohammed's latest work that was published in Bioinformatics also. Then Gatekeeper. Accelerate genome analysis like read mapping by 100x, which is substantial, but it's not enough because we want to do everything within 1 second. And starting time is maybe 2 weeks or more with a data center. So divide 2 weeks by 100, you don't get 1 second. And we're looking at in-memory DNA sequence analysis, as you can see over here. This work done by Jeremy and Damla. And more recently, this is actually a paper that's going to appear next week, which is one of the top conferences for architecture. This is a full algorithm hardware co-design, and it's Damla's next paper, as you can see. We work together with Intel folks over here, especially Intel folks. And the idea over here is to accelerate approximate string matching. And we basically redesigned the algorithm, redesigned the hardware accelerator, put the hardware accelerator close to memory. It's basically a full end-to-end algorithm hardware co-design framework to accelerate genome sequence analysis. And the results in this paper are very promising, basically. You can see that compared to even the most efficient hardware accelerators, we get more than an order of magnitude performance improvement and energy efficiency. Of course, compared to software, you're much, much faster. Compared to software, sometimes we're 3 orders of magnitude faster, for example, but software is slow anyway. Okay, if you're interested in genome analysis, we recently wrote the survey paper in IEEE Micro. It's a relatively short paper, you can see. We wrote the survey paper that talks about how important it is to accelerate genome analysis and what has been done. So it gives you a broader perspective. And if you're even more interested, you can actually see some of my lectures online that talks about genome analysis. And actually recently, one of my lecture 3 in computer architecture course was really dedicated to introduction to genome sequence analysis. And lecture 8 yesterday was given by Mohammed, who is a postdoc with me right now, was also about intelligent genome sequence analysis. So there's a lot of interesting things going on. And I believe in genome sequence. I believe genome sequence analysis is really the workload of the future. But there are other workloads, databases, graph analytics. You can see some of the workloads that we know more or less better about. They're all bottlenecked by in terms of performance and energy because they deal with a lot of data. There are other workloads in the mobile end. You can see some of the workloads that we examined for one of our papers, including machine learning inference, browsing, video playback and capture, which we're actually exercising right now. Our systems are doing video playback and capture, right? And maybe they're not doing really well since you cannot see my video on the screen. I don't know why. But one of the reasons could be data as a performance energy bottleneck. And we examined all of those workloads together with Google This is work done by my PhD student, Amirali, who is about to graduate. And we did this work together with Google. I actually spent several months at Google to do this analysis together. And we found out more than 60% of the entire system energy in those mobile workloads is spent on moving data between the processor and memory. Okay, so that doesn't sound good. So that's my third example. There are clearly many interesting things are happening today in computer architecture, but we need to also do many interesting things to solve the problems. So these are many novel concepts investigated today. We're investigating new computing paradigms, rethinking the full stack. We're looking at processing in memory, processing near data, neuromorphic computing. It's fundamentally secure and dependable computing, new accelerators, algorithm, hardware, co-designs for different workloads as we discussed, and new memories and storage systems like non-volatile main memory and intelligent memory. So increasingly demanding applications will continue to come. This is going to happen even more and more into the future. So I dream and they will come. I don't have time to tell you more stories, but I have stories related to this also. And clearly they're increasingly diverging and complex trade-offs. So today, for example, a complex arithmetic operation takes 20 picojoules. You can see the slide from 5 years ago. Give or take, the situation is still the same. And memory access is 16 nanojoules. So essentially today, memory access consumes 800x. So if you stretch it a bit, 1000x, the energy of a complex addition. So it's good to ask the question, are we really designing the right systems? Meaning, does it make sense to do a lot of memory accesses in our systems to bring the data into the computation engine? And our answer is, you should really have the capability to do processing where the data resides so that you don't do this extremely energy inefficient memory access. Okay, so past systems were looking like this. Today's systems are much more complicated, as you can see. There's a lot more components. Okay, I'm going faster than my slides are going, but modern systems are much more complicated. Okay, as a result, a computer architecture today is very different from 10 to 20 years ago. So let me conclude with these things. If I can take a couple more minutes, Ashil, I will conclude. Is that okay?
Sure.
Okay.
Sure.
So I think, given all of what I said, today there's a huge opportunity to really revolutionize the way we design our computers at the very fundamental levels, like processing. Where should processing be done? Should it be done in the CPU? No, maybe it should be done in the memory. Maybe it should be done in the storage device. Maybe it should be done somewhere distributed, right? Basically, I think it can revolutionize the way that we understand both the hardware and software and change each accordingly. And I think industry has finally realized that they're really looking across the stack. So you can actually invent new paradigms for computation, communication, and storage. And I would recommend this book. That's really nice, I think. This is a very famous book. How many people know this book, The Structure of Scientific Revolutions? I'm very curious about the answer to this, actually. Okay, Ishil knows. That's good, because she probably saw my lectures. Maybe she knew it beforehand. But I would recommend this book. This is actually a philosophy of science book that was written by Thomas Kuhn. And he wanted to analyze how big ideas in science take place. He called this as revolutions. And basically, he said that, and I think science and engineering are very similar. He gives a lot of examples from physics, chemistry, and astronomy, for example. But basically, he said that science revolves in cycles. And normal science is you have theories that explain and things. You build things in some certain way. Exceptions are anomalies. So my favorite example to this is people said the sun revolves around the earth, right? Okay, that's dogma, clearly. Okay, but maybe they found some evidence. It's a theory, basically, right? And the theory is the sun revolves around the earth. And for a long time, this theory was accepted, maybe questioned, maybe not questioned. But people who questioned them were considered exceptions. So all of these evidence in astronomy that Galileo, for example, provided were considered anomalies. And they said, okay, this is an anomaly. The sun really revolves around the earth. It's not the other way around. And if you actually said something against this, the consequences could be very bad, meaning you would die because these people would kill you, right? Because this is blasphemous. Religion also doesn't go well with science, unfortunately. Well, fortunately, maybe, because science is, in the end, has a very different method. Basically, they said this is blasphemy, right? This is an exception, so you deserve to die. Okay, but over time, even they cannot sustain that belief because there's too much evidence. There's this overwhelming evidence that shows that sun doesn't revolve around the earth. Earth revolves around the sun. And at that point, a revolution happens. You move from this pre-paradigm science. You first go into this pre-paradigm science. There's no clear consensus in the field. And then basically you re-examine the underlying assumption. And then the new theory becomes dominant. Now the Earth moves around the sun, and that theory becomes dominant. But clearly there's a lot of sweat and work that has been done to convince people that that was the case, right? Both scientifically and politically in the early times. But it's true for computer architecture also. Today, there's no dominant theory in the field. There's no clear consensus in terms of how to design the best architectures or best systems, best computing systems. There are some principles that people are examining, but people are really examining underlying assumptions. So it's a really good time to be part of this revolution that's happening in science and engineering and computing systems. And that's how you can really impact the world in a big way, I think, by understanding both the software and hardware. And by the way, this is Thomas Kuhn. I would really recommend reading this book. It's not an easy read. I'm sure there's a Turkish version that's probably easier. In the English version is not that easy, but I think it's a beautifully written book, actually. It gives you a lot of examples also. And it makes you think about the world we're living in today also, because I think, unfortunately, we're in 2020 right now. And in many ways, the way science is treated in today's world is not much different from Middle Ages. That's a bit unfortunate. That's my personal opinion, clearly. But I think we need to get rid of the thinking that's against science in the field today. Okay, but my last slide. Today, it's an exciting time to be understanding and designing computing architectures. There are many challenging and exciting platforms exist in platform design that no one has tackled or even thought about before. And I believe all of these challenges can have a huge impact on the world's future. Clearly, we're designing many, many more applications that we rely on. Self-driving cars, these drones. I mean, again, technology could be used for good or bad. The question is, of course, how do we enable this technology for the good? And maybe as a designer, we can actually enable better technologies going into the future also. Clearly, this is driven by new workloads, new applications, hunger for big data, and the fact that we can easily collect today more data than we can analyze and understand. It's also driven by significant difficulties in keeping up with that hunger at the technology layer, because we also have a lot of issues at the lower technology layers: energy, reliability, complexity, security, scalability. Okay, that's the end of what I have. So I think you're at a good point in time studying computing architecture. So hopefully you'll enjoy it. If you really want to look at the rest of the lecture, I have a recording of it actually online, because I delivered it in my class, as I mentioned earlier. But I'm happy to stay and take questions if that's what people desire, or since we're already over, we may not want to do that also.